Charles?
Yo, are you having success? Oh, well, yes, I can hear you. All right, I saw you sent some question, something.
Oh, I was just wondering if you can hear me or not. Can you hear me okay?
Yep.
Okay. I guess I just had to press the start webinar button or something.
Yeah, so you're well, you were in practice mode, which meant other people couldn't join until you went out of practice mode. So now anybody can join and go nuts.
I just want to make sure that my voice is audible.
Yep, you're good. All right, I'm gonna go away and get back to Hall of Fame.
Okay.
Have fun.
So what time do we come back? 10:15 or? A little earlier than 10:15, I
Sure.
guess.
Yeah, I think it starts at 10:15. Yeah, so yeah, a little bit before that.
Okay. All right, I'll mute myself.
Alrighty.
Thank you.
Fantastic. Cool. Thank you very much. So yes, there's the title, and there's one of my favorite spots, Manatee Springs, in just about 45 minutes from my house. Absolutely beautiful area in northern Florida. So I don't have a lot of time, I guess. I guess the 45 minutes was scheduled for the talk. I didn't realize that. But look at this ridiculous outline. Don't worry, don't worry. I'm going to skip the theory.
Hi, Sean. Sorry to interrupt you. It looks
Yeah.
like, at least on my end, that we cannot see your screen yet. So
Oh, I thought I didn't hit share. I'm an idiot.
Yeah,
Hold
we
on.
can.
I'm just, I forgot. Oh, no. It's not letting me. Oh, yeah, yes, it is. Yes, it is. Thank
there it
you.
is. Perfect.
Yeah, yeah.
Yes.
I saw this password thing pop up, but no, it's all good. So for those of you who are curious, this is a beautiful Manatee Springs. It's nearby, full of manatees, crystal clear water. And this is a ridiculous outline that I'm not going to be able to cover, but I'll leave the slides with you if you're curious.
We do have until 11:30, so you actually have plenty of time. You can.
Oh, I do. Oh, I see. I thought it was 11.
Yes.
Okay. Okay. Cool. All right, but still, I think that we won't have time for the theory. It's just there in case somebody wants to see more. We'll see. But you can see there's a lot of things. I'm sure there are many people in the audience who doesn't know what this means, who doesn't know what this means, and what doesn't know what this means. So, you know, it is a bit of a challenge. So a lot of this is a picture show. But except for this, I mean, everyone should know what stochastic approximation is. It's not as scary as people think. This is basically work with a lot of colleagues. Now, actually, I can say former students. These guys recently graduated. My former student, Yui Chen, is at NRL, and other people at NRL. A lot of the work was motivated by interactions with Andre and Emiliano and Marcello, who were all at NRL when I was on sabbatical 2 years ago. I'm partly selling my book. So in addition to making sourdough bread during COVID lockdown, I decided finally to write this book I've been thinking about for decades. I've been teaching reinforcement learning since my first sabbatical in India in the 90s. So I had tons of lecture notes and I put it together. And so I'm going to be covering mainly chapter 4 of the book today. And basically this, and also this paper, Revisiting the ODE Method for Recursive Algorithms. And so you can see more. There's a bootcamp tutorial, a 4-hour tutorial on YouTube. You can see some more. And I've got a massive bibliography at the end of this document. All right. First of all, what is stochastic approximation? I'm going to explain this crazy diagram right now. So in all sorts of problems, you can formulate the solution as a root finding problem. That's true in a lot of problems in machine learning, where F bar is just a gradient of some loss function. It's true in almost every problem in reinforcement learning. There's an approach called stochastic approximation to solve a problem like this, where you have special structure. So the function F bar is the expectation, another function, where this W here is random. Okay, and I don't think I'll be able to get very much depth in this, but I want to tell you about how you apply stochastic approximation and some refinements to RL and gradient free optimization. So here's what the ODE, I mean, what stochastic approximation is doing. So you basically think of this function F bar as a vector field for an ordinary differential equation. And you look at this differential equation and you hope it's stable. So globally asymptotically stable, meaning that every solution converges to this theta star as time goes to infinity. So you're interpreting this as a stationary point. All right, and that's like the first way of rethinking this problem. And then you say to yourself, well, is an Euler approximation appropriate? You know, is F bar Lipschitz? Because we know that if you've taken a course in ODEs, you know that these Euler approximations are effective if you choose a step size sufficiently small and F bar is Lipschitz continuous. Right? So if that's the case, then you're good to go. You get stochastic approximation. And how easy is that? You know, basically that's the motivation and the definition of what stochastic approximations are about. Okay. So what about it? So the thing to do is to realize that what we're doing is we really have our F bar there still. And basically what we've done is we've introduced noise. And we find that the ODE, the Euler approximation, and the stochastic approximation are all convergent at theta star. And the reason is that Euler approximations are highly robust to measurement error. And that's why convergence theory is now almost trivial. When I was a graduate student, it was considered very deep and difficult. Nowadays, convergence is nothing. And the theory is incredibly highly developed. And to see that, look at Vivek Borkar's monograph, and there's a second edition to appear, you can see the conditions for convergence are trivial. It almost always works. I mean, again, you need the Lipschitz continuity, you need properties of the noise, you know, the noise just being the difference between you know, these things. I mean, basically, this Wn here has the same distribution as W for all n. You need that, and you need some properties of this noise, but they're very minimal. That's exciting. What's bad is that it's slow. So stochastic approximation can be so slow, it's ridiculous. And I'm going to get into that. So the purpose of this lecture mainly is to explain to you that it can be very slow, and then talk about ways to speed it up. And in particular, for the applications I mentioned. And please scream. And somebody else keep track of questions in chat if you would, and let me know if there's something I should stop and do. So again, so I'm going to say this sort of again. Here are the steps in algorithm design. So step one is to design an ODE. Okay, so it might not be globally asymptotically stable. You might have to introduce some modifications to the ODE to make it stable. And one example of that is what's called a Newton-Raphson flow, is where you treat F bar of theta as the variable. So isn't that crazy? So I want F bar of theta to go to 0. Why did I call F bar of theta the variable? Make a change of variables. And then I could design an algorithm. There's an algorithm. My design. What a trivial design, linear dynamics. So we know that F bar of this funny theta t is equal to e to the minus t times F bar of theta 0. So we just go in a straight line to the origin. Nailed it. So that's actually a dissertation of Aditya Devraj, who recently graduated, who's now a postdoc in Stanford. It's amazing. It absolutely is amazing how all this works. And of course, it's a second order method, because in order to get a differential equation for theta t, you need the chain rule that introduces the matrix gain. So there's some complexity, but it's incredible to have a universally stable algorithm. And this is just an example. This is just an example of modifying the dynamics. All right, that's step one. So step two is gain selection. Now, this taking the step size as 1 over n typically gives an optimal convergence rate, which is 1 over n. So the mean square error goes to 0 like 1 over n under conditions. But you've got to crank up the game. And with this, you have to look at this linearization of the f bar at the theta star. But under those conditions, and more, you get this mean square convergence rate, and you can even compute this covariance matrix sigma theta. It's pretty amazing. So you got to play around with gain selection. And I'm not advocating 1/n, as I'll explain in a bit, even though it gives you the optimal rate of convergence. So here's another incredibly amazing fact. So if you haven't seen this before, just prick up your ears. You can actually compute this covariance matrix as a solution to a Lyapunov equation. And most of these things can easily be estimated. This matrix I mentioned before, this linearization matrix, there's a covariance of the noise, which I'm not going to define here. And you also get a central limit theorem and all sorts of stuff. So it's a beautiful thing that comes from free from the theory of stochastic approximation. And but there's a lot of caveats, which I'll talk about. And one is that this is the optimal rate of convergence for stochastic approximation. That's still pretty slow. Okay, so how can we improve it? Well, one thing we can do is replace.
Classroom.
Yes.
Can you maybe speak a little bit louder? We're having trouble with some audio.
Okay. I wish I brought my headphones. Yes, I will. Shall I run and get my headphones? No, probably not. I will speak louder.
Thank you.
Okay. And 1 second, I'm going to. Okay. I will try to speak louder. Okay, so this is my crash course in stochastic approximation. Design ODE. Make sure you're careful with gain selection. There's a lot more to say about this, which I don't have time to say. And then you actually can you can actually modify the algorithm. One thing you can do is try to modify the algorithm to make this covariance small. And that's the techniques to do that are well known, and there's some new techniques that are surveyed in my new book. But another thing you can do is that traditionally people often, this is Markovian or IID, and it's introduced by design, say for exploration in reinforcement learning. And tossing in IID noise can create variance and can also not be physically meaningful in some applications, which I'll explain in a second. So you can just use like smooth signals instead and reduce the variance a lot and get something that's way more applicable for some applications. And I will explain. So again, my interest is in things that maybe you don't know about. There's things called TD and Q learning, which I'm not going to define, but I'll give you numerical examples. I will define gradient free optimization. And in these applications, we create the noise primarily. And so why introduce variance if we don't have to? So the idea is that instead of this convergence rate of 1/n, we can get a convergence rate of 1/n squared. And we do that because of, if we introduce some periodic signals, their convergence rate, 1/t, integral from 0 to t, sine of t dt, that's going to 0 very fast. But, the central limit theorem gives you a 1/square root of t rate of convergence to 0. But sinusoids, things like that, converge like 1/t. And so that's why you'll get a 1/n squared when you look at the squared error. And so I'm going to change my design criteria. I'm going to again, step one will be the same. We're going to design an ODE, but step two is going to be a differential equation, and this is going to be like sine waves. For example, doesn't have to be, you know. And then we don't have to use an Euler scheme. We can use some fancy Runge-Kutta method or something like that to try to preserve the fast convergence rate that we have here. So, so that's the agenda, and which I'm going to try to explain. And am I still muffled, huh? Am I still muffled? I wonder what's going. This is the first time that's happened.
No, I think you're okay, Sean.
All right. Okay. All right. So this is my grand plan, and the idea of using this idea actually came from the finance area. I have no idea why. Maybe 20 years ago, it never really received much attention. It wasn't analyzed much, and I've worked on this on and off for a decade. I had a big breakthrough last year on getting a general theory for rates of convergence and stability for nonlinear algorithms. And I won't be, again, that's the theory section of this talk, which I won't be able to get into really. I don't think. Okay. Okay, so again, so a mixture of sinusoids is possible. Theory, this, if you look at complex exponentials, it makes theory much easier. And so in the book, I stick to that because it's so easy to prove theorems. Whatever. There's a big research area here that is just going to have to take a lot of work. One of the key things I need is I need the partial integrals to be bounded in time. So you all know that if I integrate an exponential, I get an exponential. And so that's why these partial integrals are bounded functions of time. The first integral, the second integral, and so forth. And I actually need the second integral to be bounded in time for these very sharp rate results that I can derive. Okay, so you know, you integrate a sine wave, you get a cosine wave. It's bounded. You know? So that's all I need. So this is not true if we were looking at something like a stationary stochastic process. Then you'd have growth like square root of t. All right. And more generally, I don't know if you want this, but you know, if you look at a dynamical system, you know, that's a dynamical system. It's also Markovian. It's just a deterministic Markov chain, Markov process. Well, somebody asked, does the ODE need to be time invariant? And the ODE where? Which ODE are we talking about? So this ODE does. Yeah. So an ODE that generates my probing signal. I've been calling this a probing signal. For reasons that'll be clear in a moment, this has to be time invariant. But clearly this, I mean,
Yeah, that's the one that I was referring to. The
yes. I mean, in order to even talk about, so I'm going to want 1 over t integral from 0 to t of f of theta, comma ct. I'm going to want that to converge to my f bar of theta as t goes to infinity. And for that to be true, you know, it's any time, if there was any time variance, I would stick it into the CT. Okay. And so the reason for like making these assumptions, so either assuming directly that I've got complex exponentials or assuming I've got a dynamical system, is so I can expect to get an ergodic theorem like this. Because ergodic theory holds for dynamical systems. It's not just Markov processes. All right. And so that's what I'm saying here. There's actually an invariant measure. I mean, when you have a dynamical system, there are lots of invariant measures, so that a time average can be expressed as a spatial average. There are books and books on ergodic theory for dynamical systems. So that's that. Okay. So I have a laughing emoji here. And if anybody who's known me like a long time, many at least, would know why I'm laughing, is because this equation called Poisson's equation follows me wherever I go. I swear to God, I don't chase it. It follows me. So it turns out, in order to get the results that I want for this dynamical system, I need to solve something called Poisson's equation in the Markov process literature, which I can do for complex exponentials. So I need to be able to represent integrals like this, where I'm taking a function g, I subtract off its steady state mean. I want this to be bounded. Well, very often I get more than boundedness. I can actually express it as a difference of two functions of the process. So this equation has a long history in the study of Markov processes and simulation theory, in average cost optimal control, all over the place, and nonlinear filtering, which chases me as well, and it's needed here as well in terms of the theory. You don't, for applications, you don't need it. It's for the theory to understand what you're doing. Oh yeah, no, Dora, it's not. I don't chase it. It chases me. Poisson's equation hides under my bed. I'm sorry. But you know, so anyway, this is what I've been using. It comes up in the rates of convergence results. So yeah, so when I find the optimal convergence rate, it's a function of certain Poisson's equations, which again, I won't have time to talk about too much. Okay, so gradient-free optimization. So what I'm going to do is I'm just going to jump to applications, since I don't think we'll have much time for the theory. So I was always told it's hopeless, and I always believed that. I don't believe that anymore. I think gradient-free optimization can be practical. And some motivation is for optimizing the grid. So basically, like trying to regulate voltage in a distribution level. Maybe you have a complex simulator that's very reliable. Your models maybe aren't that good. So you can simulate and just look at input-output behavior and optimize using the methods I've talked about. When I was at NREL, one application we were considering was trying to optimize the pitch angles and the direction of wind farms, and do this by putting in these sinusoidal exploration signals. So these wind farms, you know, each turbine moves back and forth, maybe in a sinusoidal fashion. That's physically reasonable. Putting in white noise to a wind farm makes no sense. These gradient-free methods I'm going to describe are perfectly adapted to physical systems like these. So this goes back to Kiefer and Wolfowitz. I'm not going to describe what they did back in the 50s. The goal is to minimize some loss function over Euclidean space. And Kiefer and Wolfowitz had some very complex algorithms for trying to do that without knowing the gradient. So you could only observe the loss function of particular values of theta. You had no idea what the gradient was, or it was too complex to compute. Spall was a big hero in making it much simpler. One of his more famous examples is something that looks like an Euler, an approximation to a standard approximation to a derivative, where you take the loss function and you add on epsilon times white noise, and then you subtract epsilon times white noise, and then divide by 2 epsilon. And if you do a Taylor series expansion, you'll see that the even terms cancel. And what you're left with is a gradient sticking out there. times this little w, right? The w is a variable here, w transpose. And that's why you multiply by w here. Because when you multiply by w, you end up with a w transpose, which is a rank 1 but positive semi-definite matrix in front of the gradient. Okay, so this is what Spall introduced in the 90s. And W is an RD. Okay, and that's one of millions of algorithms. There's a lot of similar algorithms out there. And so what you end up getting is that the mean dynamics are given by this F bar here. So when you take the expectation of this, you end up with this. And you can design the covariance to be anything you want, make it the identity matrix, okay? And so you can design G as well. All right. And it's been known to be quite slow, okay? But I think the reason is that there was a lack of understanding of convergence rate theory back in the 90s. And so people didn't apply the wonderful acceleration techniques that were known, but only in a select, small mathematical community. And what's really cool is also in the 90s was all this beautiful control theory called extreme seeking control, which claims to have a history going back to the 1920s. I won't get into that now, but there's these wonderful block diagrams. There's references here. Kristich is one of the heroes in this area, where they came up with wonderful techniques for gradient free optimization based on all sorts of filtering and modulation, blah, blah, blah. But again, they didn't have any theory to understand the rates of convergence either. And now I'm very excited in the last year, there's all these new tools to try to address rates of convergence and accelerate these techniques. Okay. And what's great, they introduced low pass filtering. That is so similar to averaging techniques that go back to the 80s. So they were sort of reinventing some of the averaging theory that was already there in stochastic settings. So it's fun. Okay, so basically what I'm going to do is I'm going to put a little cue here for quasi whenever I want to make something non-random. This would be the quasi stochastic approximation version of Spall's two evaluation algorithm. Okay, and it kicks ass. So here's an example. So here's a function, a loss function I'd like to minimize. I cook this up to be non-convex. And so the optimal, the theta star is sitting here. That's the minimum of this function of theta. All right, and this is 2 dimensions, but it's great for illustration. And if you look at loss as a function of time, it's massive, And if you look at the algorithm, you can see it settles down to a limit cycle because I chose alpha t constant. And so it failed, right, everybody? So you can see the trajectory. This is theta t. It's just oscillating around. No convergence. But what I mean by averaging is just average. And it turns out that when you do this averaging, you get the answer. It's almost perfect. So basically, you basically compute the optimal solution exactly. And so what's shown here is this average loss as a function of time, and it's right on top of the actual optimal value. It's just amazing how averaging works. just absolutely amazing. And there's, so the book, all of chapter 4 is devoted to, illustrating this and explaining why. I don't know why he's got fuzzy suddenly. They'll come back. What do I do this maybe? Yeah. Anyway, so this is an example of how you can make these things work. And always remember this trick. So basically, apply high gain and 2 average. Now, I don't recommend constant gains because it's too hard to tune. So having a slowly decaying gain is a good idea. But you don't want it to go to, so 1/t is a bad idea, actually, in general. So not 1/t, even though that's suggested in some of the literature. Okay. All right, that's just an example. So again, I'm just going to give another example. So the same approaches to control. And I'm just going to go through a simple example. So this is a famous example of Rich Sutton. So Rich here refers to Rich Sutton. So he has this very simple model of a car trying to go up a big hill. Oh, somebody asked, how about high gain causing adaptation instability? Absolutely. So the reason I do not recommend a constant step size, it was just for this example, is that you don't know if it's going to be stable or not. Well, if you let it decay, you do. So it's way more robust to allow AT to go to 0 slowly. So no, all of my algorithm is Lipschitz continuous. So I'm assuming somebody asked if I have discontinuities. So in recent work, I do have theory for stochastic approximation and quasi-stochastic approximation with discontinuities, but all the elegant theories for Lipschitz continuous functions. All the rate theory in particular is for Lipschitz continuous functions. So I'm just going to give an example again. So, so basically, he has an example that really has just one hill, and the idea is that you have limited acceleration you can apply. So you have a very weak car, and so the only way to get to the top of the hill is to oscillate back and forth. You go full speed this direction and full speed this direction and back and forth. And the question is, what's the feedback law that will get you to the top of the hill in minimum time? And so it's a standard example that people use to try things out. Let's see where I got this done. Yeah. And these are just examples of some threshold policies. Yeah, so I mean, this is a threshold policy where basically yeah, I'll give you a definition in a moment. So again, the goal is to minimize the travel time to the destination, which is denoted J of X. So that's a value function. It's a very simple one, just time to reach the destination. What we're going to do is our loss function is we're going to have a family of policies. So the theta corresponds to the policy that's applied. And I'm going to try to minimize the subjective function. The reason for putting this max in is that I can't be guaranteed that I'll ever reach the destination. So you have to do something to make sure you have a finite value loss function. Okay, so I'm going to pick initial conditions created in this sort of quasi-stochastic approximation setting as well. And this j theta of x is the cost from that initial condition x. All right. And so again, we can just apply this brute force, don't even have to think about it. Just go through and do it. And I'm just going to explain how you do it. I'm not explaining the policy, I don't think. Maybe I have it here. So we have a model. Z is position. And velocity is v. And of course, you know, when we put our foot of the gas, we accelerate. So that's what we're seeing here. And when we actually can, you know, accelerate backwards, put the car in reverse, and that's why you can be we can go backwards and accelerate backwards. UK equals 1 or minus 1. You know, we know it's going to be a bang-bang control solution because we're not putting any cost on you. Okay, so yeah, so I do have it here, thank God. So here's a threshold policy that whenever I'm far from the goal, then I just accelerate to the goal at maximum speed. So I've got this hill, and I've got my parameter theta here. And I put in a v. I added this on. VK is so small it doesn't really matter. You can ignore the VK there. But roughly speaking, there's some region here where I always have u equals 1. And then over here, I have u equals the sine of v. Yeah. So in this region, whatever direction I'm going, I just keep accelerating that direction maximum speed. It's a reasonable thing to do. It's often stable. So that's just something you could try. So how do you optimize over that class? All right. And so we can use these just really off-the-shelf technique, and it works. Okay, so we can use in the book. My first option is what I call QSGD number 1. This is actually, I take my probing signal. I'm writing this down discrete time for simplicity. Now I'm just adding on I have an observation, my current estimate. I add on epsilon times noise, and I multiply the whole thing by noise. Again, this Cn is an RD. But here d is equal to 1, just for simplicity. Now, each of these has dangers. This is a bit dangerous. It's not Lipschitz continuous. This is dangerous. Can anybody see why this is dangerous? Well, this is dangerous because I'm taking a difference of my observations, and then I'm dividing by epsilon. And so this can be killed by measurement noise. With measurement noise. And so in the book, I really sort of push this more than this other one. That's why this gets a number 3. It's sort of my least favorite if I'm actually taking the observations from reality. If it's purely a simulation, then this is fine. Okay. But in this case, it is Lipschitz because I'm on a compact domain. So this is really, really fun. Okay. And I've got a slight extension here because I'm doing 2 things. My L of theta n plus epsilon times probing I'm manipulating two things simultaneously. I'm perturbing the theta that appears. So I'm perturbing the theta that appears in my policy, and I'm also perturbing the initial condition. And I'm doing them both simultaneously just for fun, just to illustrate the theory. All right, and it kicks ass. It works perfectly. So when you look at the final run, it doesn't give you the optimal estimate, but the objective function is so flat. This I should make that bigger. I'll make this bigger for you. This objective function is so flat that it doesn't, of course, it's not going to find it exactly. So you end up with sort of this histogram, which is a box, and you end up always, it's insanely reliable after only, just 1,000 iterations. You're dead on right. Well, if you look at the standard algorithm, you get incredibly unreliable algorithm. You get just with the same variance parameters, everything's sort of set up the same. The trajectories just go all over the place. So about half the time, you get a good estimate, and then often you get crazy outliers. Now, if you spend enough time tweaking parameters, you can make this work. But there's lots of theory to say this is much, much, much better and more reliable. Okay. So those are the examples. Any questions on that? You can code this up in a second. A couple of lines of code.
Sean, can I ask a very quick question?
Yes.
So the theta not converging to theta star, is this somehow related to the persistency of excitation of the noise that you're designing?
Oh yeah, good point. No, I'm not saying it doesn't converge. So it is. So theorem, the limit as n goes to infinity of theta n is equal to theta star. So it does work, right? It's just that the question is how fast, right? And so here we see that basically what we end up finding is that in 5,000 iterations, we're close enough so we could declare success. Well,
the plot that you're showing, that trajectory is almost parallel to the theta star line. So
yeah, it's going to be very, very slow, and that's because this is so flat. Yeah. So you'd really have to crank up the gain. If you wanted to get faster convergence, you would need a higher gain near theta star. Okay. In reinforcement learning terms, 5,000 is a very small number of iterations.
Mm.
Yeah. I forgot what I used here for the step size. I'll have to go back and look at that.
But that's what you were saying before, right? If I understood correctly, that you design the noise dynamics in such a way so that you increase the convergence.
Absolutely. And so here, oh yeah, I mean, definitely, if you let me play with this long enough, I could make this into a point mass with 5,000 iterations. If I play around with cranking up the gain in just the right way and then average the results. Yeah, but here, yeah. When you see this flat behavior, this suggests the gain is too small. When a good algorithm oscillates around the optimal value. So, yeah, this has not been optimized. I haven't even talked about optimizing. All I've done is mention averaging. I haven't talked about how to really optimize theta convergence. Because I know this is supposed to be an introduction. It's really hard to pack it all in. So what time do we end?
Michael,
what should I do? Yeah.
Michael, when do we need to end?
11:30.
Oh, really? I've got all that time?
Yeah,
Well, in that case, I will walk through some of the theory, not all of it. But let me talk about how it could be helpful to see what's going on.
If you want to leave a few minutes for questions at the
Oh, I
end.
definitely do. So I'm not going to take a half an hour. Absolutely. No, 25 minutes. No, I'm going to just take 15 minutes to go over some high points. So, yeah, this is really useful. So basically, in terms of stability theory, if we do choose this gain here, we're going to get the 1/t convergence rate, but only if we crank up the gain again. So we need G big. All right. And so for the example I just showed, because the function's so flat, that's why we need a G. Okay. And that's why, so it's not a good idea. All right. Usually. And most of the time I would avoid 1/t. Even though if you heard me give a lecture 2 years ago, I'd be saying UT, we get 1/t convergence rate. That's optimal. There's a lot of new theory that makes me realize, maybe not. So in terms of analysis, what you do is you take the error between the quasi-stochastic approximation and the solution to an ODE with the noise removed. Just analysis, okay? So what you do is you take those two things, you take the difference and you divide by AT. I'm going to show this bounded. All right, and basically, here in the book, I just took this special case. And I'm going to convince you that rho equals 0.6 is going to be great. Yeah, I mean, awesome. Now, oh, Jesus, you're crazy, Sean. Now you're getting a t to the 0.6 convergence rate. That's awful. Then you're going back to the stochastic setting. Well, don't forget, we can average. These averaging techniques work in the deterministic setting as well, sometimes. All right, and so you get an ODE, which is just brilliant. You end up with this linearization matrix I mentioned before. You get this bizarre thing here, which is zero mean. And then you get this strange thing. You end up getting the derivative of the log of AT, you know. But what's cool is that that's just big O of 1/t. This thing here. And so you can ignore it if you know, again, if that AT equals 1/1 plus t for the rho, if rho is less than 1, then this just becomes some bit of noise you can just ignore. It's irrelevant. Okay, so then we only need A star Hurwitz. So that's the conclusion from this. So that was really exciting to be able to derive this ODE. That's very, very nice. And so yeah, this is just basically emphasizing that fact. That we get a really cute ODE when rho is less than 1. We get this nasty term here that comes out if rho equals 1. That's right. And that G inverse comes from the fact that we're dividing. And again, I'm taking this special case. I've got a G in there. You see, I stuck in a G. That's what we're seeing a G inverse. All right, so there it is. And so, so it's not that hard to derive this ODE. And then it's a little bit hard to deal with the fact that you've got this additive noise. But those of you who know a bit about state space control, you can come up with some transformations. And I don't think I should go into it. Well, there it is. You make a change of state variables, let yt equal to zt minus the noise, and you get a differential equation where you don't have additive noise because this is insignificant. Okay, so this is just playing around with the equations. You get these pretty formulas. So again, we're looking at understanding this normalized thing. So imagine we start out with a nonlinear differential equation, and we end up being able to easily justify a linear approximation that comes for free. It's just absolutely wonderful. And all your linear system theory comes into play. And so now you can just apply quasi-stochastic approximation theory to this thing here. And we can see that T is going to converge as T goes to infinity. And we get the rate of convergence with that. So QSA 101, even though it's a very new area, tells us that yt is equal to some limit, y bar, where the mystery comes in. And that's where Poisson's equation comes in. I didn't look for it. It came to me. And y bar has such a complex expression, I wouldn't even try to tell you what it means. Now, so what I'm going to do is just tell you the implications. I'm going to get rid of all this. Forget all this stuff. Forget it, forget it, forget it. Right there. So the conclusion here is, what about my averaging? Well, sadly, what happens is that this y bar gets in the way. And so we don't get the convergence rate we want. We only get the 1/t convergence rate if this y bar is equal to 0. So we need a new filter. So instead of averaging, we do some more sophisticated filtering. We can kill y bar. But for quasi-stochastic gradient descent, y bar is just big O of epsilon. So it's really not that big a deal. So there it's okay. Oh, A star is not symmetric. No, A star is just Hurwitz. That's all we care about. Yeah. And if A star is not Hurwitz, you're in trouble. I mean, you've got to change your problem somehow. You've got all sorts of difficulties if the linearization is not Hurwitz. So there's a lot of stuff here. So so again, for quasi-stochastic gradient, luckily we have this this result, and so averaging still is effective. Right? So there's the theory. It's quite pretty. Okay, so conclusions. Number one is just that, is that why add IID noise when we don't have to? I mean, we can add nice smooth, especially in a physical system. So I'm fascinated about translation. So all the theory has been in continuous time. And so when I translate, now I have discrete time quasi-random signals. So anybody who's working in quasi-Monte Carlo will say, come to me, I can solve your problems. I think not. I think maybe they're wrong. Okay, that's not said out of arrogance. I'm just really intrigued that maybe you can do something dumb like sine waves, which anybody in quasi-Monte Carlo would say, no, 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 we've proved that's wrong. It's numerically terrible. Don't ever do it. It's stupid. But don't forget, we've got really firm theory in continuous time. Why not talk to OD experts and you do a really sophisticated OD translation? So instead of investing all this energy in designing pseudorandom numbers, just do a better job of translating OD. That's a possible, it'll be fun. And there's lots of recent work in machine learning that backs me up, which I could talk about if it was time. There's applications to constrained optimization, which I've worked on some. Applications to RL I've worked on as well, as I've mentioned, but I hate to lose all the beautiful techniques. There's so many wonderful ideas in RL that you lose in the QSA setting, so I don't know what to do about that. Tackling dimension, I've got another smiling emoji. People love to say that they're working with theta in dimension 1 million. They handle that by doing that block, coordinate descent. So we can just do the same thing. I don't know. I don't know if that's really a research area, but there's all sorts of other techniques for acceleration, which is a great research direction. And I hope that I get to optimize the wind for Colorado. Wouldn't that be cool? It'd be so much fun to try this stuff out in a real big application. I don't know if that's the best, but something. Distribution feeder. But you can see that's it, except for advertisements. All the rest of these pages are just millions of references, if you're interested. And my time is up. Thank you.
Thank you.
Oh, the question here, yeah.
We will open it up for Q&A. So if anyone has a question for our speaker, maybe you can just type it in the chat and I can read it on your behalf. Or if you want to speak up, maybe Michael can coordinate the Q&A.
And already there's only a question there.
Yeah, I was just wondering, these two questions
from you. Yeah.
So the A star does not need to have real eigenvalues, right? No?
No, they can be complex and you have all the intuition you have in that case.
Okay.
Yeah.
And the other question I had is that, just to keeping on adding these different filters in my loop, like the filters that you're adding.
Yeah.
So do these filters have to be fast so that they don't collide with the time constant of my plan?
No, what's funny is they don't. And the reason is that, the linear system, converges exponentially quickly. Where am I? Where's my differential equation? Oh, right there. So, without the AT, we'd get this exponential convergence. Well, right here. So, theta bar. Well, that's not it. How do I say this? Oh, yeah. Theta bar T goes, that's not quite right. Oh yeah, theta bar goes to theta star much faster than 1/T. Much faster. I mean, if rho is less than 1. And so
my question wasn't exactly that. My question was that when I add additional filters in the loop, so essentially I'm adding more and more integrators, right?
Yeah.
How does that collide with the stability of the closed loop given the time constant and all that?
Well, it's just that there's no stability. We're just trying. Oh, you have the algorithm. It's just that our goal, 1/T is optimal but very slow. You know what I mean? So 1/T is the best. A sine wave is the gold standard. The rate of convergence of its average is 1/T. So we know we can't do better than 1/T. And all these filters don't hurt the 1/T convergence. Yeah. So yeah.
Okay.
It's just our goals are so different than user control.
Any other questions for Sean?
So we had one quick question here. Can you show the books on the last slide?
Oh yeah. Oh sure.
Most important slide, right?
Oh, that's right. This is it. Zapdos is right there. That is a Pokemon Zapdos.
Wonderful.
Yeah.
I had one quick question on this slide, on the side. You talked a little bit about some applications. Can you elaborate on what applications this works very well for, and then maybe something that it doesn't, and what the hurdle would be, or what the big adjustment would have to be?
Well, I mean, so well, let me see. Let me give an example, like in the context of optimization. So consider, here's a failure of both quasi-stochastic gradient descent and gradient free. So both of them. I mean, so basically, I mean, I can't imagine why you don't use sine waves when you can, or something. So that, you know, I don't know yet why you would ever not use pseudo-random numbers when you can. But the question is about gradient-free optimization. We lose second-order methods. We lose ZAP, which is what I call the Newton. Well, we lose second-order methods. And I don't know of any way to claim them. So I saw a recent paper by Florian Döffler on optimizing a distribution feeder, and his results were so fast, it was insane. It was because he was using Newton-Raphson. I don't know. I have no idea how to get that kind of rates using gradient-free techniques. That's the one sad thing. I have no idea how to do that. But besides that, I don't know. I think it's a free lunch. You know, does that answer your question?
Yeah, for sure. Thanks.
Yeah.
Yeah, just curious,
Yeah.
like that,
Yeah.
what we can get back, or what's unrecoverable.
Yeah.
There's
Yeah,
nothing.
Again, this makes me super sad because I love second-order methods. Yeah.
So that was it from this side.
Yeah.
I don't think there's anything else in the chat.
So to carry on from the previous question from Michael, so Sean, besides extremum seeking control, can you say a little bit about how gradient-free optimization and gradient-free RL that you talked about, how they can be made more suitable for designing nonlinear controllers in general?
Oh yeah, but I mean, just in general, it's I mean, well, also in terms of what I described before is called an actor method. For the for my example, and so there's also what's called actor critic, which is fully stochastic. And it's an example of what I'm saying, we're losing a beautiful tool, okay? But Ben Recht made headlines and he actually reinvented Spall's algorithm. He wasn't aware of Spall's work. So in this paper that he became very famous. I mean, he was already very well known in RL, but he became got a lot of notoriety on this paper showing this sort of primitive technique that I described today, beating this was considered a very sophisticated actor critic method. And see his work. I mean, you can whenever you have, if you have, excuse me, UK equals some policy parameterized by theta of xk, you can always apply method 1. See the book. It's plug and play. It's just completely trivial. I mean, you saw how simple the code is. It's just it's a few lines of code, and so you basically just modulate theta. All you're doing is you're applying u and cranking theta up and down, and then have this outer loop, and you can then find at least a local minimum. So basically you'll get theta star may only be a local minimum. So Benedict was only looking at LQR, but he found it was very efficient. This method 1 for LQR, well, the method 2 just failed completely.
Okay. Any other questions from the audience? From the grad students, postdocs? I think some of them are meeting you later in the afternoon to have a one-on-one. But
oh, good. Oh, is there a new schedule? I didn't notice that.
no, the schedule remains the same, like the one that we sent you yesterday. But
Okay, great.
yeah. Michael, is there any question from that side? No.
Nothing on our side.
Okay, if there are no more questions, let's thank the speaker one more time for a very informative talk. So thanks, Sean. I'm giving you like a virtual.
Yeah, I know it's funny, isn't it? I can hear the roars of applause. Don't worry.
I know. All right, so Michael, do I end the meeting now, or what's the protocol here?
Yep, you could just end the Zoom.
Okay.
So I'll go. Well, hold on before you do, and then I'm gonna. Do I go back in with my old link for the meetings?
Can you say that again?
And so then I just go back to my previous link for me.
Yeah, the others.
We'll make sure. Okay.
Because you have meetings with the individual people. So. Okay. Thank you, Sean. Thanks again for the great.
Thank you. Great to see you. Bye.